Hi everyone, welcome to part 3 of chapter 2. Last time we talked a lot about how electrons are arranged in atoms. We used orbital diagrams, which were the lines and arrows, to show how those electrons were arranged, and we also used the electron configuration and that abbreviated electron configuration with the noble gas to show how those electrons were arranged in the atom, kind of more on paper. We used that then to talk about valence electrons, which were those electrons in the outermost energy level, and then we started using Lewis dot structures to show the valence electrons. We covered a lot of ground last time, so make sure you feel really solid on all of those topics before moving on to this one. Today, we're going to use that information to talk more about periodic trends, and then we are also going to talk about ions. Ions are charged particles and they are super important in chemistry. So lots to cover today. Let's get going. All right, so the first thing we are going to talk about are periodic trends. We've already talked about a few different periodic trends without calling it that. I've told you quite a few times that the periodic table is the world's greatest cheat sheet, right? It has a ton of information contained on it if only you know how to read it. So we are going to learn how the periodic table shows us periodic trends today. We're going to look at atomic radius, ionization energy, and electron affinity. And again, it's all laid out right there on the periodic table. So these periodic trends that we're going to talk about permit us to predict chemical properties and the reactivity of elements. So based on where these elements are on the periodic table, it tells us a bit about how they react. Are they in that very first column with only one valence electron? And those are called the alkali metals, right? And they react a certain way. And if we go to the far opposite side, we have the noble gases, and they're actually pretty unreactive, right? So where they are on the periodic table tells us about how they react and other chemical properties. So one of these chemical properties that's displayed on the periodic table is the atomic radius. So essentially, we're just going to talk about the size of the atom. The way that they describe the size is the distance from the valence electron, right? So that electron in the outermost energy level to the nucleus. So essentially, if we're talking about, just kind of an atom, and here's all of its valence electrons, if there's an electron way out here, it's this distance, right? So it's essentially half the distance across the entire atom, which is why it's called the radius, just like you would call it a radius in math, okay? So if you look at this periodic table, the biggest element down here that's shown on this periodic table is rubidium. And actually the largest element would be directly below it, which is not pictured, and that's francium. Okay, so atomic size, if we look at our alkali metals, gets bigger going down, right? From hydrogen to lithium to sodium to potassium to rubidium, right? We're getting bigger and bigger and bigger and bigger. We're going to talk why that is in just a minute. But as we go from left to right across the periodic table, you'll notice that the element is getting smaller. And I want you to make a note of this one because that's not something that we would really predict. And we'll talk more about that on the next slide. Okay, so our general trend. Our atomic radius increases going down a group. So as we go down, it's getting bigger, right? It's getting larger as we go down a group. But it decreases from left to right across a period. Okay, so going down a group, the reason it gets bigger, I think, is pretty straightforward. If here's our nucleus, as we go down a group on the periodic table, we're adding on shells, we're adding on energy levels. So as we go down, we're just kind of adding rings, essentially, around our atom. So it makes sense that it's getting bigger and bigger and bigger because we're adding on electrons that are farther and farther from the nucleus. They're in shells that are at a greater distance from the nucleus than ones on the inside. So I think this one makes sense, right? This whole going down a group makes a lot of sense that it's getting bigger because the electrons are farther from the nucleus. The one that I think isn't as logical is going across a period. And again, it's getting smaller as we go across a period, which I think, initially you might not realize. Usually, if we, go back a slide, as we go from left to right, so as we go this way, people think, okay, well, we're adding on protons, We're adding on neutrons, we're adding on electrons, so it should get bigger. And I think that's pretty sound logic. Like if you were just kind of thinking about it from that standpoint, you're adding stuff to our atom, so why isn't it getting bigger? Why is it getting smaller from left to right? Well, the reason is that our atomic number is increasing from left to right. So our number of protons is getting bigger, okay? As we get more protons, we're increasing what's called the nuclear charge. So if you hear that term, essentially it's just telling us the number of protons is getting bigger. There's more positive charge in the middle. So we're increasing the positive charge in our nucleus, but we're not adding on more electrons or more electron shells. So we're adding positive charge in our nucleus, but the added electrons are all going into the same energy level. So they're not getting farther from the nucleus, they're all just kind of adding to this ring. So as we add electrons to the same energy level, and as we add more protons to the middle, there's greater attraction in toward the nucleus. Okay, so that greater attraction actually serves to kind of shrink our atom. So instead of getting bigger when we're adding protons and electrons, it gets smaller because there's an increased attraction between the nucleus and those electrons in the outermost energy level. So again, I think, once we start talking about it, I think this starts to make more sense, right? You can think about it as magnets. We're putting like a bigger magnet in the middle, and we're putting more magnets in the same distance around the outside, which is pulling this shell in closer to the nucleus and shrinking our atom. So again, as we go from left to right across a period, it's getting smaller because we have more protons in the middle and more electrons to the same energy level. That's key. And that's causing a decrease in our radius. All right, our next periodic trend is ionization energy. Ionization energy is going to be really important once we start talking about ions. Okay, ionization energy is the energy it takes to remove a valence electron. So again, if we're thinking about our atom, okay, it's the energy it takes to pull an electron off of this outermost energy level. So we have this shown here. This is the orbital diagram for sodium. Okay, sodium has 1s2, 2s2, 2p6, and 3s1. You'll notice that this orbital diagram is written in boxes instead of as lines. That's okay. You'll also see that it's written from left to right instead of up and down. I've done this to kind of save space on this slide, but please always draw our orbital diagrams up and down like we learned in the previous lecture. Okay, so here's our electron configuration for sodium here on the left. If we were going to remove an electron, the one that's going to get removed is this 3s electron. Remember that 3 is telling you that electron is in the third energy level. So it's the one that's farthest out from the nucleus, whereas the 1 and the 2s are all much closer to the nucleus. Those are core electrons. So this 3s electron is our valence electron, and there's just one of them there. So the ionization energy is the energy needed to remove that electron. So as you see, it's gone here. So what's shown above is when we remove that electron, it makes Na plus and E minus. That E minus is our electron, and our sodium is now positively charged because it lost one. We're going to talk more about this in just a little bit. But essentially, like I said, ionization energy is the energy it takes to remove a valence electron. And I want to be really clear, when we talk about ionization energies, we're going to talk about things that have high ionization energy or low ionization energy. If an atom has a high ionization energy, that means it's really hard to remove an electron. That means that electron is bound really, really, really tightly to that atom. It's attracted to the nucleus. Okay, and so that would make it harder to remove. You can think about ionization energy as kind of the cost to remove an electron. If it has a high ionization energy, you can think about it as being like a high energy price. It costs a lot of energy to remove that electron, whereas something with a low energy is more of a low energy cost. It's easy to pull that electron off. So generally the way this works, as we go down a group, so as we are going down, our ionization energy will decrease, okay? And as we go from left to right across a period, it will increase, okay? So let's talk about these. As we go down a group, so the way that this looks, right, again, as we go down a group, those electrons are farther and farther and farther from the nucleus. And the farther that electron is from the nucleus, the easier it is to remove, right? Remember, this nucleus is positively charged. And so this electron, since it's negative, is attracted to the nucleus, okay? But the farther and farther and farther out it is, the less attraction it feels to the nucleus, simply because it's farther away. So if we put on electrons that are way, way out, right, they're not very attracted to the nucleus, so they have a low ionization energy. So the bigger our atom is, the lower the ionization energy, because that valence electron is so far from the nucleus, it's not really experiencing an attraction. When we go from left to right across a period, remember our atom was getting smaller. Okay, and since our atom is getting smaller, those valence electrons are closer to the nucleus. And when they're closer to the nucleus, that makes them harder to remove. Okay, so as we go from left to right, the atom gets smaller, so that makes it a higher ionization energy. Okay, so this all has to do with atom size. If an atom is really big, that means it has a low ionization energy because it's easy to remove an electron that's really far from the nucleus. But if that atom is really small, then that electron is being bound really tightly to the nucleus, making it really hard to remove. So you can think about ionization energy being inversely related to atom size. Our last periodic trend that we're going to talk about today is electron affinity. And so electron affinity is essentially the opposite of ionization energy. Ionization energy is the energy it takes to remove an electron, whereas an electron affinity is the ability of an atom to gain an electron. Okay, so these are essentially opposites. Atoms at the far right of the periodic table, so like fluorine, have a really, really high ionization energy. Not ionization energy. Well, they do have a high ionization energy, but they also have a really high electron affinity. So when we talk about electron affinity, we are actually not going to talk about the noble gases. The reason for this is that noble gases don't gain electrons. Okay, remember we talked about the fact that noble gases are unreactive, and the reason for this is that they have a complete outer shell. Remember, they have 8 valence electrons, except for helium, which has 2. But the rest of them have 8 valence electrons, and 8 is kind of a magic number in chemistry when we talk about bonding. We're going to get into this whole rule called the octet rule, where all of the atoms are trying to get to 8 valence electrons. Since these noble gases already have 8 valence electrons, they're not trying to gain any more, which is why we essentially set their electron affinity as 0. However, these ones next to them, right, these are the halogens. The halogens have an extremely high electron affinity because they have 7 valence electrons. They are really, really close to having 8 valence electrons. And because of this, they have an extremely high electron affinity. They want to gain an electron so that they can have 8, just like these noble gases. So as we go from left to right across a periodic table, our electron affinity increases because we're increasing the number of valence electrons, we are decreasing our atom size, and we're making it so that that atom really wants to gain an electron. Okay? All right, I want you to go ahead and get some practice on this. So we have 3 questions here. I want you to pause, answer these 3 questions, and then come back when you're ready to see the answer. Alrighty. Whoop. Let's go over this. So which of these elements has a larger atomic radius? So first off, let's find potassium. and bromine. So there's potassium and bromine. Remember that the atoms are getting smaller when we go from left to right. Remember, we are adding on more protons to the nucleus and more electrons to that same energy level, so our atom gets smaller as we go from left to right. So our larger element here is potassium. Okay. All right, now let's find boron and indium. So here's boron, and here's indium. So when we're thinking about atomic radius, as we go down the periodic table, we're adding on more and more and more energy levels, which makes our atom larger and larger and larger. For this reason, indium is greater than boron. Okay, so now let's talk about electron affinity. So when we're looking at electron affinity, remember electron affinity is going to increase from left to right. So bromine will have a greater electron affinity than potassium. And I realized just now that we didn't talk about up and down on electron affinity. But essentially, it's the same as ionization energy. As we go up, we are getting an increased ionization energy. So boron will have a greater electron affinity than indium. Okay? And then finally, ionization energy. Ionization energy and electron affinity have the same trends. So if you know the answer for ionization energy, it's going to be the same for electron affinity. But remember, the smaller our atom is, the greater the ionization energy. So since bromine is smaller than potassium, it has a greater ionization energy than potassium does. Because remember, the smaller that atom is, the tighter it's holding on to that electron. And then if we compare boron and indium, again, boron is our smaller atom, so it's going to hold on to its valence electrons more tightly, making it have a larger ionization energy. All right, go ahead and pause here and find that Chapter 2 lecture worksheet. Complete problems number 24 through 35, and then come back when you're ready to move on. Alrighty, so now we're going to shift gears away from periodic trends, and we are going to talk about ions. Ions are really important in chemistry. So much of our chemistry has to do with ions, and ions are just charged atoms or charged groups of atoms. So thus far in this course, we've talked about neutral atoms, right? We said the number of protons equals the number of electrons, making our atom neutral. And so whenever we talk about just kind of atoms in general, we're talking about neutral atoms. But when I say ions, that means something that has a charge. It's not neutral anymore. Okay, these ions can be positively charged or negatively charged. When it's positively charged, we call it a cation. Okay, and if it's negatively charged, we are going to call it an anion. And we're going to go through what cations and anions are as we move through this. Okay, but this is just a bit of terminology here. Positively charged, called a cation. Negatively charged, called an anion. Alrighty, so as we move into ions, just a brief review. Remember that the particles that make up an atom have a charge, right? They are either positively charged or negatively charged. The positive stuff, remember we were calling a proton, and things that are negatively charged, we call electrons. If we have a neutral atom, the number of positive charges and negative charges are equal. So the positives and negatives cancel out, and they give us a neutral charge. And so we say our net charge is 0. So we just don't talk about the charge at all. So remember, all of our protons are in the middle with the neutrons, which I've left out for now because they don't really matter when we're talking about charge. So all of the protons are in the nucleus with those imaginary neutrons for now, and the electrons are on the outside in that electron cloud. This is super important. Only electrons can be added or taken away. Remember, if we change the number of protons, we change what atom it is. And we can't do that. That breaks laws of chemistry. The only things that we can do are add or remove electrons. Okay? So this particular atom has 5 protons in the middle and 5 electrons. So right now, this atom is neutral because the positives and the negatives are equal. However, if we add an electron, right? I just added one here. Now we have 5 protons and we have 6 electrons. So they're not canceling out anymore, right? 5 protons and 6 electrons is not equal. So our overall charge is a 1 minus. We have 1 extra electron, so our charge is 1 minus because we have 1 extra negative charge, right? These 5 protons in the middle are canceling out these 5 electrons, but we have 1 negative electron left over, giving us a 1 minus charge. And I want to make it really clear, when you're writing these charges, the number goes first and then the charge. I know it's a little bit nitpicky, but if you put the charge first before the number, that means something else in chemistry. Not in this class, we won't get to that, but it means something else in chemistry. So try and get into the good habit of writing the number and then the charge. All right, here's another one. So now we have 5 protons and only 3 electrons. So our charge here is a 2 plus, right? Those 3 electrons are canceling out 3 of the protons, but we have 2 protons left over. We have 2 positive charges left over, so our atom has a 2 plus charge. So when we are removing electrons, like we just did in this last example, the resulting charge is positive. Okay, so I want you to make a note of this. When you are losing electrons, the atom becomes positive. A lot of times people think, okay, I'm losing something, that makes it negative. No, you're losing electrons, right? Which means you're going to end up having extra protons, so your charge is positive. Okay, you can also think about it if you're trying to have a way to remember it. You're subtracting a negative, essentially, right? We're removing electrons, so we're subtracting a negative, so our atom becomes positive. So if you want to remember it that way, I think that's probably a little bit helpful. So this atom here went from neutral, where our positives and negatives canceled out, to a 1 plus because it lost an electron, meaning it has 1 proton left over. Okay, so here's your rationale. It becomes positive because the atom now has more protons than it has electrons. This charge is telling you which extra thing you have. So we have 1 extra positive charge, 1 extra proton. All right, so now let's do the opposite. When we are adding electrons, then our whole atom becomes negatively charged because we're going to have extra negatively charged stuff, right? We're going to have extra electrons. So this atom here is going from neutral to a 2 minus because we have 2 extra electrons that are not being canceled out. So again, remember, this charge is telling you how many extra you have and what charge they are. So it's telling us I have 2 extra negative charges, 2 extra electrons. Okay, so our atom is negative because we have more electrons than we have protons. Okay, so do try and keep these straight. Either way though, an atom with a positive or a negative charge is called an ion, just in general. That's a really kind of general term that we use to talk about anything with a charge. So if it's neutral, we'll call it an atom, but if it's charged, we'll call it an ion. Okay? And again, remember, only the number of electrons can change. It can be added or subtracted, but only the electrons can change. And remember, the number of protons in an atom never changes because that will change what element it is, and we can't do that. All right, let's talk about our 2 different kinds of ions. So our first type of ion is a cation. Okay, and so I want you to look. It's a cat ion, like a kitty cat. This is not pronounced cation. Don't say cation. Everyone will laugh at you. This is pronounced cation. Okay, So cations are positive ions. And remember, there are more protons than electrons. This happens when the atom loses electrons. So if it loses electrons, it forms a cation. It forms a positively charged ion. And when we name these cations, which we will do, the name stays the same. So it doesn't reflect any charge. So it goes from calcium to calcium. Nothing happens to the name of our cation. So the way that I remember that cations are positive ions, and you're going to laugh, is that cats have paws. So our ions with a positive charge are cations. So there you go. Kitty cat ions, right? They have a positive charge. If that didn't make you smile or you think it's silly, if you look at cations, right, that word, this T kind of looks like a plus sign. So you can remember that cations are positive because there's a plus sign in the word. Or you can remember cations are positive because cats have paws. That's what I like. All right, so let's look at an example. If we have a neutral potassium atom, so remember, atom tells us it's neutral. That means it has 19 protons and 19 electrons. The way we know it has 19 protons is because potassium is atomic number 19. If you have your periodic table next to you, look at potassium, it's atomic number 19, so it has 19 protons, and if it's neutral, it also has 19 electrons. To form the cation, we will actually remove one electron. Then we have 19 protons and only 18 electrons. So we have one extra proton. So it makes the formula K+. So our neutral potassium was just K, but if it's a cation, it becomes K+. You'll notice that it's not K1+. We don't write the 1. In chemistry in general, we just don't write ones. So instead of writing K1+, we just write K+. So this is what it would look like. And when we remove that valence electron, our atom, you'll notice in this picture, actually becomes smaller because we've removed a valence electron, which shrunk our atom. Okay. Our atoms can also lose multiple electrons. So they don't have to just lose one electron. They can lose 2 electrons. They can lose 3 electrons. And this will actually depend on how many valence electrons it has. If you look at your periodic table, you will see that potassium is an alkali metal. It only has 1 valence electron. So when it loses electrons, it just loses that 1 valence electron. If you look at magnesium, magnesium has 2 valence electrons. So when it makes a cation, it loses both of those valence electrons, and then it will form a 2+. If you look at aluminum, aluminum has 3 valence electrons. So when it forms a cation, it loses all 3 of those to form a 3+. Okay, so the number of electrons these atoms will lose is actually based on the number of valence electrons it has. And we'll talk about more about that in just a little bit. And then remember, our cations are named the same as their parent ions. So a neutral potassium is just called potassium, and when it loses an electron, we call it a potassium ion. But nothing happened to that name. And the same thing for magnesium and aluminum. So it's not saying, right, there's nothing that's happening to this other than we added the term ion. And you'll notice the name doesn't say anything about how many electrons it lost either. We know how many electrons it lost by how many valence electrons it started with. But again, we'll talk more about that in just a little bit. Let's talk about anions. Anions are negatively charged ions. Okay, this means there are more electrons than there are protons, right? They're not equal anymore. It has a negative charge because it gained an electron. So it has 1 extra electron or 2 extra electrons, which is why it's negative. The name of our anions change to end in IDE. So if it's chlorine, it becomes chloride. Okay, so that's how we will know it's an anion and not a cation. The name of our cations stays the same, but the name of our anions change to end in IDE. So chlorine becomes chloride, fluorine becomes fluoride, or iodine becomes iodide, right? So they end with IDE. So I had my cute little, kitty cation, so that you could remember that cations are positive because cats have paws. I don't have one as cute for this. It was kind of a stretch. If you put a negative ion together right here, and then you cross out the negative, you get anion. That's the best I got, guys. I also kind of think that anion kind of looks like the word onion, and onions give you bad breath, which is a negative thing. I know that's kind of a stretch too. Honestly, what I do, I remember cations are positive because cats have paws. Therefore, anions are negative because cations were positive, right? And that's kind of how I go about it. Also, I want to point out this is anion, not anion. Be very careful, anion. All right, so let's look at an example. So a neutral chlorine atom contains 17 protons and 17 electrons. So like I said, if that periodic table is next to you, check out chlorine. It's atomic number 17, which means it has 17 protons and 17 electrons when it's neutral. So chlorine actually has 7 valence electrons. And remember, in chemistry, that magic number is 8. So when chlorine forms an ion, it gains 1 electron so that it has 8. Okay, so when it gains that 1 electron, now we have 17 protons and 18 electrons. So now, instead of being a neutral chlorine atom, we have Cl minus. Okay, and remember, we're not going to write ones in chemistry. So even though it's Cl1 minus, we just write Cl minus. Okay. So when chlorine gains a valence electron, it becomes bigger, right? It goes from 17 electrons to 18 electrons, and as it gains, it will become a larger atom. All right, and like I said, all of our anions, when they gain an electron, they become an anion, and we change our name to end in IDE. So fluorine becomes fluoride, and chlorine becomes chloride. And that's how we know it's negatively charged. It ends in IDE. So positively charged atoms, we don't change their name, but negatively charged atoms, we do. All right, so again, here's the name of some common cations. You'll notice all of their names stay the same, whereas our anions, their names change to end in IDE. Another thing I want you to notice is that our metals are the ones that form cations, and our nonmetals are the ones that form anions. This will be really important as we move into bonding in the next chapter. Okay? Metals form cations. They lose electrons to form positively charged ions, whereas nonmetals gain electrons to form negatively charged ions. All right, so the reason that atoms gain and lose electrons is to become like their nearest noble gas. Okay, so essentially, right, lithium has 1 valence electron, and if it loses 1 electron, it becomes like helium. All of these, right, sodium, magnesium, and aluminum, their nearest noble gas is neon. So they will lose their valence electrons to become like neon. The reason these atoms want to be like a noble gas is because noble gases have 8 valence electrons. Okay, they have what's called a complete outer shell or a complete octet. So these atoms want to lose electrons to be just like the noble gases and also have 8 valence electrons. For the same reason, these nonmetals will gain electrons to become like their noble gas. Okay, so like if we look at nitrogen, and you can look on your periodic table too, nitrogen has 5 valence electrons. So it needs to gain 3 in order to become like neon. So that's why nitrogen has a 3- charge. Oxygen has 6 valence electrons. So it needs to gain 2 to become like neon. So that's why it has a 2- charge. And then fluorine has 7 valence electrons. So it just needs to gain 1. So it has a 1- charge. So the number of valence electrons will tell us how many electrons our atom needs to gain or lose to become like the nearest noble gas, right? If it has 3 valence electrons, it will lose 3 to become like its nearest noble gas. If it has 5, it will gain some to become like its nearest noble gas. Okay? You'll notice I've left out the column that has 4 valence electrons. Okay? Otherwise, we have 1, 2, 3 valence electrons, 5, 6, 7. Okay, so the reason that 4 isn't on there is because the ones in group 4, they do a different type of bonding. So we're going to ignore them for now. They essentially don't really make ions, so we're not going to talk about them at the moment. But if our atom has 3 or fewer valence electrons, so 1, 2, or 3, it's going to lose valence electrons and make a cation. If it has 5 or greater valence electrons, then it will gain valence electrons to become an anion like its noble gas. Okay? So 3 or fewer will lose, 5 or larger will gain. Okay? All right. So remember we were talking about periodic trends and how we can, use the periodic table to see those trends. We can also use the periodic table to see our ion charges, which is awesome. Okay? All of the elements in group 1A, so these are our alkali metals, all of the elements in group A will make a 1+ charge because they all have 1 valence electron, so they all will lose that 1 valence electron to try and be like their nearest noble gas, so they get a 1+ charge. All of the elements in group 2A, so those are our alkaline earth metals, they all have 2 valence electrons, so they will lose those 2 valence electrons and make a 2+ charge. All of them in group 3A, which is also called group 13, they all have 3 valence electrons. They will lose those 3 and make a 3+ charge. And so remember, this group 4A in the middle is missing because that group 4A does a different type of bonding altogether, and we won't talk about them when we talk about ions. But if we skip over to group 5A, they all have 5 valence electrons. They need to gain 3 more to get to 8, so they all form a 3- charge. Group 6A all has 6 valence electrons. They need to get 2 more to get to 8, so they all form a 2- charge. And group 7A, those are our halogens. They need to gain 1 more to get to 8, so they all have a 1- charge. This is going to be super helpful for you. So I would recommend writing this down. I've got it shown here on the periodic table though, which I think makes it a little bit more clear. So remember, metals are the ones forming cations. So here are our metalloids. Remember our metalloids go along that zigzag line. Everything this way, these are our metals, okay? They are going to form cations, okay? So all of these here, remember, all of those have a one valence electron, so they're going to lose that 1 and form a 1+ charge. So what I want you to do is on your periodic table, and actually, please make this is not quite right, please put 1+ above this, okay? Same thing here, all of these will form a 2+ charge because they have 2 valence electrons, so they're going to lose those 2 to make a 2+ charge. We're not going to worry about the transition metals right now. The transition metals kind of do a different thing, and we'll talk more about them in a little bit. We're going to skip over here. These ones that have 3 valence electrons, they are all going to form a 3+ charge. Okay, so if they have 1 valence electron, 2, or 3, they are going to lose all of those valence electrons and form a cation. The transition metals, the reason that I don't talk about them when we're talking about periodic trends right now is because they can actually lose different amounts of electrons. They're still going to make cations because they're still metals, but some of these could lose 1 valence electron, or it could lose 2, or it could lose 3, right? And it can lose different amounts. So we'll talk more about those transition metals in a little bit since they don't follow a pattern. All right, so now let's talk about anions. Let me change this real quick. All right, so let's talk about anions. Non-metals form anions. So it's all of this stuff on the right side of the periodic table. Remember, these are metalloids, so the stuff to the right of the metalloids are going to form anions. Okay, so these all have 5 valence electrons, so they need to gain 3, so they're going to form a 3 minus charge. All of the next one have 6 valence electrons, so they need to gain 2, and they're going to form a 2 minus charge. And then the halogens have 7 valence electrons, so they need to gain 1 to have a 1 minus charge. Remember, everybody's trying to get 8 valence electrons. The noble gases over here do not form ions because they already have 8 valence electrons. There's no reason for them to gain or lose electrons because they already have that magic number. They already have 8, so they are satisfied. Alrighty, go ahead and pause here and work on problems number 36 to 49 on the Chapter 2 lecture worksheet. Otherwise, keep working hard, and I will talk to you guys next time.